I have put online solutions to questions 11 and 13, homework questions. So if you go there, you'll see a PDF where I take you through every step I can think of how you would get the answers to those two. And hopefully that'll get you by our first section. It's been a bit slow, but things like that happen. Next section is going to go really quickly because there's very little to it. It's just number crunching, which kind of makes life a little bit easier because you just need to know what's the formula and what you're going to do. So what are the last two techniques that we use to find areas under curves numerically? They're called the trapezoid rule and they're called the Simpson's rule. And I think there's 4 or 5 questions in this section, the homework, because it's really just number crunching, as I said. So imagine you had a graph like this and you don't know the formula, but you use the value of the function at these points and you make your usual table. So you're either given a table and you're asked to use trapezoid or Simpson's rule, or you're given a graph, and this graph, you get the table from it and then you go off and you do it. So how does the trapezoid work? Well, in this particular case, as you can see, we're going to do 1, 2, 3, 4, 5, 6 strips. And we're going to start at 3 and we're going to finish at 15. Well, you break it into the typical strips, and we've kind of done, you would think, every combination that you could possibly think of, right? We've done use the left side, we've done use the right side, we've also done a guy that you use the fill in the middle, right? The midpoint note. So we've got all these different rectangles, and you might think, well, that's it. Well, no, that's not it. We've got the trapezoid rule, and they just change the rules. Can you imagine joining a straight line from that dot to that dot? So what you end up making is not a rectangle, but a funny little shape that looks like that. It's basically a rectangle with a little triangle stuck on top. That shape is called a trapezoid. So in this picture here, can you imagine that I join the start and the finish with a little straight line? Won't I make lots of little trapezoids? And what I do now is I add up the area of those little trapezoids, and some other person, thankfully, has figured out that there's a formula for doing that without you physically having to do 6 separate calculations. If you find them all and add them up, you get a guy called T6. 6 strips, T for trapezoid, T6. The formula is delta x over 2. Delta x, that guy there, you get that by the usual start, takeaway, finish divided by n. You get 2. So it's delta x divided by 2. The value of the function f naught. And then 2 of everybody in the middle. And then you finish with only one version of the guy in the other. So it's very often called the 1, 2, 2 rule. 1, 2 of everybody in the middle, 1 at the end. So if you want to find the area of all these little trapezoids and add them up, this formula here will do it for you. Right, delta x is 2 divided by 2. It's one of these, 2, 2, 2, 2, 2, and one of these. So I could probably do that in my head. So here goes. One of those guys, 2 of that height, 2 of that height, 2 of that height, 2 of that one, 2 of that one, and you finish with 1. So you notice it's 1, 2, 2, 2, 2, 2, 1. That's the pattern. Right, it's a bit boring, right? But it's not hard to do, right? You take the first number, right, the value of the function at the first point, double all those guys in the middle and 1 at the end, add the whole thing up and multiply by delta x over 2. Right, now in this case, 2 over 2 gets me 1. And if I add this up, what do I get? 4, 6, 14, 25. So put down a 5, carry 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 18, 19, 20. I get 205. And there we go. The area under this curve, starting at 3 and finishing at 5, is 205, whatever it is, square units. So the trapezoid rule, typically a table. If you don't get a table, you'll get a picture like this, which you will make the table from. And then you just go delta x divided by 2, one of these, 2 of them, one of these. So that seems reasonably straightforward. It's just follow the process. This is how you do it. If you follow the process, you will be able to get a good estimate for the area under this curve. Now, we already know some guys. I'm not going to, couldn't have used this table to get an L6 or an R6. Right? Could have done that. I couldn't use this table, but I could have used this diagram. Could you imagine that I could have got an M6, right? I could have done that. Right, we've got a new guy in town called T6. The worst case scenario are these guys. These guys do not give a very good answer for whatever number of strips. You might wonder, between these two guys, which one tends to do a better job? And you might think that it's a trapezoid, but it's not. L6 and R6 are the worst. T6 is a little bit better, at least it's better than them. But midpoint 6 is better than everybody. So there's one interesting property. Here's another one that you probably wouldn't have guessed. Do you know if you find a left 6 and a right 6 and you add them together and you divide it by 2? Can you imagine doing that? Finding this answer, finding that answer, adding them up and divided by 2? Do you know that is the same thing as T6? You can check it out, but it does. It is. It's kind of interesting. So you could have said that T6 is just the average of L6 and R6. I guess if you were really wanting to make your life hard, couldn't you find L6 and R6 the usual way and then average them out, right? Add them and half it and you'd get the same answer. But it is better. So we like it. You know, for the same number of strips, it's a little bit more work, but it is more accurate. So what am I going to do next? Well, I'm just going to show you the last guy. What does a Simpsons rule look like? Well, we're going to call it S6. That's not a surprise. S for Simpson. It's delta x over 3. And now the formula gets a little bit messy. You use that guy once. You use that guy 4 times. You use the next one once. You use the next guy 4 times. The next guy twice. The next guy 4 times. And then the last guy once. So what does that look like? The pattern is 1, 4, 2, 4, 2, 4, 1. So what you do is you use the first guy once, you use the last guy once, and everybody in the middle goes 4, 2, 4, 2, 4, 2 until you reach the end guy. So you start with the first guy once, and then you go 4 times, 2 times, 4 times, 2 times, until you hit the last guy, and the last guy will be a 1. So in this particular calculation, what would Simpson's 6 look like? Well, it would be delta x, which is 2, divided by 3, 1 of the first guy, 4 of the next guy, 2 of the next guy, 4 of the next guy, 2 of the next guy, 4 of the next guy, and finish with 1 of the last guy. And that I'm definitely not going to try. In my head, 10, add 48, add 30, add 64, add 38, and a 92, and a 25. And the answer is 2/3 of 307, which is times 2 divided by 3, and I get the answer 204.67, which is not that different from this guy over here. You agree? They're very similar. Simpson's rule has this weird 1, 4, 2, 4 thing, right? 1, and then you go 4, 2, 4, 2 until you finish. Another thing about Simpson's rule, n must be even. But nobody's ever going to give you a Simpson's rule question where it wouldn't be even, because that would be unfair. But it has to be even for the pattern to work. And
the function has to be even?
No, the number of strips have to be even. So
okay.
You can only do it with 6 strips, 8 strips, 10 strips. You couldn't do Simpson's rule with 5 strips. The pattern doesn't work with 5. It's not a major constraint. I mean, it wouldn't be that hard, wouldn't it, to pick an even number of strips instead of just a random odd one. And as I say, in a typical question, they make sure it's even, so you wouldn't even know that it was an issue, because they're only going to do it in those situations. And this little fellow over here, do you know that Simpson's rule is by far the most accurate estimate for the same number of strips? You know, sometimes you do left and right, you do 20 strips, and you're only good to about maybe 1 decimal place. See, if you did 20 strips with Simpson's rule, for a lot of questions, your answer would be good to 3 or 4 decimal places. It is that good an estimate. So if you only had one method to estimate the area under a curve, whether it's the data is given as a table or as a diagram that you create into a table, you should always pick S6 or whatever the strip number is. It's more work, but it's also more accurate.
Is there a specific reason for the 4-2-4-2 pattern, or is it just...
It is just the sheer math behind it. I'm sure if you went online, they would prove it to you. If you want to know what geometrically is happening, it's even weirder. Do you know that in the Simpsons rule, when you took a strip, you basically got a little guy called a trapezium, right? It looked like that. If you take a strip from Simpson's rule, right? So there's your start point and there's your finish. What they do in Simpson's rule is that they join these 2 points together with a quadratic curve.
It's a little strange.
It's very strange, but it's not as obviously curved as I've done. Very often the quadratic curve just looks like that, right? It's hardly got a curve at all in it. And it works better. It just does. It's kind of interesting why it works better. But it does. I suppose maybe, and this isn't a reason, but it's my reason in my head, is that would you agree that when you do a normal curve, even when it's like this, when you join the 2 points together, it's never perfectly straight. Isn't there always going to be a little bit of curve in it?
Probably.
And a quadratic is a little bit of a curve. So maybe it's going to fit a little bit better because you curve the 2 points being joined rather than straight line the 2 points being joined. I mean, it's as good an excuse as any for why it works, but it does. Are we good with this two processes? Because basically your questions are all going to be the same. Here is a table, find T6, S6, L6, M6, whatever they're asking, right? Or here is a graph, use the graph to get the numbers and then do the same question. Do you want me to do another table with a T something and an S something? Or can we call this section done?
I'm good.
You feel good? Right. Everything I've done here will remain the same. When it's trapezium, the pattern is the first guy, twice everybody else, and one of the last guy. When it's Simpson, it's the first guy, 4, 2, 4, 2, 4, and finish with one of the last guy. And remember the delta x over 3 for the Simpson, and the delta x over 2 for trapezium, or the trapezoidal. I'm going to call that good then, unless someone has a question. I guess you'll find out when you do it whether you have a problem, in which case you can, contact me. So,
Professor,
yes.
were we going to go over question 4 in the homework?
Question 4, let's do that right now before I move on now. Yes, we shall now do it. Give me a few moments to find the right guy. Yeah, when you look at question 4, it's should be called 4, isn't it? Let me make sure I got the right one. Right. Okay, I'll go out and you tell me if this is the one you're talking about. Have we got anything in chat? This thing that we've just done right now is 7-7. Did you say question 4? Someone else is saying we're working on 7-7 right now. So the first question is, where does Simpson's rule and trapezoid rule questions are? Where are they? They're in the section 7-7 homework. I think there's 4 or 5 homework questions. There's not many. And the question 4 that I was asked to do, I believe that's from 5-1. Is that correct?
Yep.
Right, so that's what I'm going to get set up now. It should be in here. And here is the guy. Now, you're going to get distracted by the fact there's a whole load of stuff, which is basically the answer next to it, but let's just show you what's going on here. Here is the curve. It's been split into a whole number of strips, as you'd expect. And there's a little find the region under this curve 5x squared on the interval 0 to 4 and show the sum and so on and get this guy. And so now we're working through a whole, it's kind of worked example where they're showing it and you just fill in some missing pieces. Right. So it talks about, let me get your picture out of the way. The Rn, right, the right hand sum, is the area of n rectangles, each of which is 4 over n wide. Now if you're wondering where the 4 over n comes from, it's b, 4, take away a, 0, divided by n, so that's 4 over n. And the function height is 5x squared. So you're going to find the guy at these particular x values, 4, 8, 12, all the way to the last one. And that makes the height of the rectangles, because the function is 5x squared. Then when you use this fella, so I guess that would be like the first rectangle, its height would be 5 over 4n squared. And then the next one would be that. And you get all of this. So Rn is height times width, which is what all that is. And if you pull the 5 and the 4 together, you get 20. So what goes in here? Well, right. So what goes in here would be 16 over n squared. You'll say, well, where the heck does that come from? Well, if you look carefully, do you see that there's a 4 there and then the square? And then you've got all these guys, so it's 16 over n squared. Then the next missing number or term goes here, And the answer is, so it's a bit distracting because you're seeing the answer, but essentially, if you take this piece and you multiply it by that piece, that's where this came from. So that's what goes in there. They then tell you that all these fellas here are equal to that. So if you take this guy, so you just repeat the answer here, put it in there, and you multiply it by that guy, this is what you end up with. So if you take this horrible expression here and you multiply it by this fella here, and you tidy it up a little bit, that's what you get. And then you take that answer and you put it in here. They pull out a common factor of 160 because 320 over 6 gets you this horrible mess. That guy goes here. These two guys here simplify down this way. Personally, I wouldn't do it that way, but it works. And you eventually get that answer times 2, gives you this one. Now that is one of those horrible generalized versions. And I will leave this up for a few seconds because what you can do is go back and look at the video, pause on this page, and then you can just use these results. I don't want to spend any more time working on these very specific questions, but hopefully you've got enough time to just keep notice this guy and then you should be good. What I will show you is, oh, I haven't made it visible yet. If you go here, I have all the working that you would need to question 11, or at least my version of it. And then all the working that you would need to do question 13. So what I've done here is given you another example of one of those very general questions. The one that we just left, the book made a bit of a meal of it. This question 13 is pretty much the same question, but I've just written it down, I think, in a little bit clearer form. So you want to get your head around these general Riemann sums. I'd probably look at how I did question 13, because that makes, in my opinion anyway, it makes a bit clearer what the heck's going on. Now, I hope at least I've given you enough to get that question done. And that's it. So, we are finished with number crunching. We are finished, for the most part, with general Riemann sums. We are very slowly, but thankfully, reaching the good stuff. So, let's return to our problem. We want to find the area under the curve, this guy. We have done every numeric technique in the book. We've even done this weird Riemann algebra thing full of sigmas and n squareds to get the answer. Neither of which are very practical. Wouldn't it be nicer if there was a better, easier way to do all that work? The analogy would be, you remember in Calc 1 where you spent forever in a day finding f dashed of 5 by doing the limit as h tends to 0 and 20 minutes work or 5 minutes work. And you finally got the answer, it was 2x squared, right? And then we said, hey guys, here's a shortcut. Well, that's where we're going to start beginning that creation of the shortcut. First technique we're going to look at is geometry. What does it mean? Well, there are certain shapes, not many, but there are certain shapes that we can actually get the area under the curve using just geometry, just using, I know how to find areas of shapes. The first one is straight lines.
Your screen is pointing at you right now.
Thank you. Okay, so first one is straight lines. Suppose this fella is that, or if you prefer, f of x equals 2x plus 1, right? And suppose I was interested in the area between 1 and 3. Would you agree that I should be able to find that area without doing weird algebra, you know, Riemann sums? And I want to get an exact answer, so there's no point in me doing any of the numerical techniques for the most part, because they won't typically give you a perfect answer, they'll just give you an accurate estimate, but that's it. Well, here goes. In geometry, isn't that point 3? Isn't this point, 7? So the distance between here and here is what, 2? If I slice this shape into 2 bits, would you agree that I get a 2 by 3, which is a 6? So that rectangle is 6. And then I get a 2 by 4, and a triangle whose 2 by 4 is a half of 2 times 4 gets me 4. And so I could tell you what the area is. Does that seem reasonable, that if it's a straight line, I could basically just do something like this, break it into a rectangle and a triangle, find the 2 areas, and if you add them together, isn't that the perfect area, right? It's not an estimate, that's the real area. That makes sense? Straight lines. There are not many of these guys, but there are some. Oops. I won't even tell you what the equation is, it actually doesn't matter. But what I want to know is the area under this curve. Essentially, I want to know that area. This shape is half a circle. So if you want to get its area, don't you do a half pi r squared? So you do a half of pi. What's the radius of this circle, or half circle? 5. Right. So it's a half times 5 squared. What's that? 25 pi over 2. And normally you leave things as exact values. So 25 pi over 2 is the answer we want. Don't go to your calculator and go 25 times, what, 3.14 divided by 2, because pi isn't just 3.14. That would be an estimate if you did that. So far, so good. So if it's a straight line, I can get the area under the curve. If it's a half circle or a quarter circle, I could get the area under the curve. What's left? Not much, actually. You might get a shape which doesn't even have a formula, but nobody cares. But it looks something like this. That goes to 4. That goes to 10. That goes to there. And then that goes to there. And I'll put in some other numbers because I'll need them. 8, 12, 14. There. So if you were being asked to find the area under this curve, well, I know it's straight lines, but we'll call it a curve. The area under this weird shape, wouldn't you basically just find the area of each piece and add them up? Right, now I'm going to call this piece A, this piece in the middle B, and this piece at the end C. And I'm going to write down what their areas are. And then the whole area is basically what you get when you add them up. Right, if I wanted to do A, wouldn't it be the same straight line trick that we used before? I would just break it into an 8 by 4 rectangle, so that bit's 32, and an 8 by 6 triangle, and an 8 by 6 triangle is 24. So that one adds up to, what's that, 56. Right, this piece in the middle looks a bit like an archway to me. Would it seem reasonable that the best way to do this one would be just to split it into a big rectangle and half a circle? That seem reasonable? To get the whole thing? So what we got? 4 units by 10 units tall. So that would have an area of 40. This is half a circle up here, right? What's the radius of this half circle?
2.
2. Right. Can you imagine the distance from here to here would be 2 and it would be 2 that side? That help? Right. Now, if it was a whole circle, wouldn't it be pi times 2 squared, which is what, 4 pi, agreed? If that was a whole circle. But again, isn't it only half a circle? So we get half of that, which is half of that, which means its area is 2 pi. So 40 plus 2 pi. Oops, changing colour. And the baby one at the end, isn't that just one big rectangle? 2 units by 10 units. So the total area would be this plus this plus this. That's 116 plus 2 pi. So if you were given a find the exact area under a curve, if it's a picture, it's very easy. If it was an equation, I guess you could just draw the picture and then you'd know what it was. But as long as it's only straight lines and half circles or quarter circles, we can get the exact area. Any questions about that? Does that seem, compared to what we've done, almost baby work, right? Yeah, I could have done that when I was 10. Right? I can find areas of things like that, add them up, I'm good. So let's show you some notation. The area under the curve from A to B of this function is described by this symbol, the integral from A to B of f of x dx. That's the notation that we use to tell people we're finding the area under a curve. It's called the integral from A to B of whatever the function is, dx. Do you see that f of x dx? Doesn't that kind of come from the Riemann sum, you know, the sigma fxi delta x thing? So if you're wondering why that notation works. So if I was doing this question here, I would call it the integral from 1 to 3 of 2x plus 1 dx. So that would be the notation for this, and of course the answer we found was 10. In this case here, it would be the integral from 0 to 10 of whatever the function happened to be called, dx. And for this one here, it would be the integral from 0 to 14 of f of x dx. Do you feel comfortable about what we've been doing for the last 10 minutes or so? If I gave you a shape like these and said, I want you to find the area under the curve, would you say, yeah, I could do that? It's just geometry. Are you comfortable with the notation that we tend to use to represent that? Now here's something. Suppose I tell you the integral from 1 to 3 of some function, we don't really care what it is, and I tell you that the area under that curve was 12. And I asked you to use that to find the area under a function three times f of x. If the world was a nice place and things were sensible, right, easy to do, wouldn't it be nice if you could just pull out that 3 as a common factor and say that this should be the same value as this? Wouldn't that be nice if that was true? So if I tell you that the integral from 1 to 3 is 12, the integral from 1 to 3 of 3 times it should be 3 times 12. And it is. Suppose I tell you the integral from 2 to 5 of g of x is 7. Right, so you're told that. I could use that to find the integral from 2 to 5, not of g of x, but whatever 2g of x. Can you imagine g of x was x squared? Then wouldn't 2 of g of x just be 2x squared? Now, you can pull out 2 as a common factor. And now you have 2 times 7, which is 14. Suppose I tell you the integral from 1 to 2 of x squared dx. Suppose I told you I know somehow or other I figured it out. The exact value of that. If you give me a few seconds, I'll actually tell you what it is, because I know the shortcut. It's 7/3. Suppose I just told you that. What would be the integral of that if you knew that? Can you see that
7.
all I've done here is multiply this thing by 3, right? And according to what I've done in these examples, if you multiply, don't you just pull it out? And 3 times 7/3 is 7. Okay, try a different one then. What would that fella be then? Or at least tell me how to get that fella. How would I get the exact area under the curve of 5x squared if I knew the area under the curve of x squared was this number?
Would it be 35 over 3?
Yeah, it'd be 5 times 7/3. It'd be 35 over 3. I'm doing one more until I think we've got this. I'll probably be killing, what's that phrase? Flogging a dead horse. Suppose I wanted to know the integral of 10x squared. Won't it be 10 times 7/3? Right, 10 times this guy. And that would be 70/3. What this tells us is, if we can find the area of this guy, can't we then use it to find the area of any multiple of this guy? I can use it to find the area of 10x squared, 2x squared, 43 billion x squared. As long as I know this thing, as long as you tell me, that guy. You don't need to wonder yet, where did that 7/3 come from? It's magic. Somebody just tells you it's true and you use it. You can now get some other fellas. Suppose I tell you the integral from, let's change ones. 1 to 5 of f of x is 7. And the integral from 4 to 5 of another function called g of x, and that answer is 12. I should be able to find what the answer to this function would be. Great. If you're told this, you should be able to find that. So what would it, how would I go about that? What would it be equal to?
Or
It
you
would
just
be 21 plus 24, which would be 45.
Yeah. I mean, it is kind of intuitive, isn't it, really? If I've got a building block, some information to start with, can't I build bigger and bigger walls? Just by putting pieces together and saying, right, if you know the building block, you know what these two are, can't you get this one and any multiple? And as long as it's a number, right, as long as it's 4 times this or 5 times that or 2 times this, it's going to work. You will be able to get your answer. So that means we now have another technique for getting the exact area under a curve. We started off with the geometric ones, right? If it's a straight line or a half a circle, we can get the area under the curve in those graphical questions. If it's made up of, I tell you some things, you can use that to generate the next bunch of questions. For about the next 6 minutes or so, I'm going to go and look at the homework for you. And we're going to see, hopefully, what that looks like. I don't want that. I want section 5.2. So if you're wondering what we've been doing lately, it's section 5.2. Okay, now I don't know, can you see the homework question 2 that I'm looking at right now?
No.
No, okay.
no.
So I'm going to go out and in so that we can see it then. Okay, let's look at our first homework question. Let me take, well, it doesn't matter. The answers are there. These questions change anyway. But it is distracting to me to see an answer. So hopefully that'll go away. Yeah, good. Right. Here we have I'm calling them curves, right? Here we have a curve going straight line, half a circle, straight line, right? And we're being asked to find the area of these fellas, right? Question A says the integral from 0 to 2 of this function g of x. If you're looking at 0 to 2, aren't you basically looking at that little triangle there? You agree? Now, I know how to get triangles. Isn't it half base times height? Can we just say, I hope we can say, that that's 4? You agree?
Mm-hmm.
Okay. I guess I'm not. Yeah, I wish we were in class, because if I was in class, I'd just see your faces. But I can only see about 3 or 4 of your faces, and if you look tired or worried, it makes me think you're not getting it. But it might just mean you're tired, and this is really easy, and I'm making a meal of it. Okay, if you look at the integral from 2, which is here, to 6, which is here, isn't that half a circle?
Yeah.
And would you agree that that circle has a radius of 2? Is it pretty obvious how the centre? So wouldn't if it was the whole circle, it'd be pi times 2 squared, which is 4 pi. Since it's only a half circle, isn't it 2 pi? And here is a mistake. 2 pi. I think I hit pi. Go on, pi. There. And you might say, I don't see any mistake there. Right? Half of 4 pi is 2 pi. Where is your mistake? Here is my mistake. And this is not intuitive, but it's the first time it's happened.
It's negative.
It's negative. In integration, that's essentially the jargon for this Calc 2. In integration, if the curve is below the line, the area is negative, and if it's above the line, it is positive. And I know that you think of area, we would normally say to you before today, perhaps, look, guys, you can't get negative areas, right? But actually, you can. But now we're telling you it's okay. we didn't want to tell you that before Calc 2, because then wouldn't you be putting the answer, the area of that field is -4, because you thought negatives were okay. Right, I'll be back in Calc 1. Negative areas did not make sense. In fact, in real life, it doesn't make sense. So why does it make sense in Calc 2? Because very often what we are calling areas, which is what this is, they also have a physical definition, and one of them could be displacement. And so you could have a negative displacement, couldn't you? Where up is positive and down is negative. Can you imagine a journey where you finished lower down than you started? So it's totally okay to be negative. And the little guy at the end, 0 to 7. Well, won't 0 be start here and finish here? So in that little piece at the end there, would you agree that little piece at the end there is a positive a half? So what would I get? I'd get 4.5 and this guy. So 4.5 would be a fraction. So we would call that 9/2 minus 2 pi. We cool with that little hiccup? The areas are allowed to be negative. Can I do this without screwing up too much? Let me show you something that is kind of cool to do with area under curves. Here is the sine function from 0 to 2 pi. I know the area, right, the integral from 0 to 2 pi of this function. Because of symmetry, won't this bit, even although I don't know what its size is, won't it be equal and opposite to that bit? So won't that make this answer 0? So I don't know what that is. I don't know what that is, but I know that they're the same thing, whatever that is. And so they cancel. So that was a cool little thing. Right. So I'll return back for, oh, no, I won't. You're going to do attendance because we've got a few moments, and you're going to say hi to me to get your attendance. And while that is happening, we'll finish off with the joke then. Has anybody here got a really bad, corny joke for me? Harrison, have you got one?
I've got one.
Oh, go for it, James. What you got?
Well, okay, I had one. It was a joke about a deflated wheel, but I think it's a little flat.
Oh,
That's pretty corny. That's pretty corny.
Oh,
that's
God.
pretty corny.
Oh, but I like it. No, that's good.
It's
I
good.
like
It's
that.
short. It's really short.
I don't mind short.
It's good.
Right, okay, we're on really old jokes, but what do you do with a very sick chemist?
I don't know.
If you can't cure him, you bury him. If you've done chemistry, that joke might be vaguely funny. Okay, great. I think as a recap, and then we'll finish here. What we've learned today, what I hope we've learned today, is that 7-7 is basically just follow the formula and you're good to go, right? If it's trapezium, it's 1, 2, 2, 2, 2, and finish with a 1. If it's Simpson's rule, it's 1, 4, 2, 4, 2, and finish with a 1. Just grab your calculator. There's no shortcut. It's boring, but it's pretty obvious. And then for the second part today, I hope we've got that you can find the exact area under curves depending on the information. If they give you a picture and it's made up of straight lines and halves of circles, you can use geometry, right? If they tell you the area from 0 to 4 is 22, can't you use that information to get the exact area of 3 times f of x or 4 times g of x, or any combination of them? And that's pretty much most of what that section's about. When we come tomorrow, we'll maybe look a little bit more at the homework and a little fiddly bit at the start. And then we actually do, if we have time, fingers crossed, we'll get there. We will show you the shortcut, which is not bad, because when you did Calc 1, it probably was week 3 before you saw the shortcut, wasn't it? So at least it's going to be the start of week 2 or the end of week 1 where you finally get to see the shortcut, which means that once we show you it, you'll be able to find the area under any curve you like. And you won't have to do number crunching. Okay, that's it. Have a nice day, everyone. If you've got a question that you want to ask, I guess hang about for a few minutes at the end. I'll try and answer that.